Okay, next speaker is Hadi Erturk. We talk about comparing complexity measures with nested sampling.
Yes. So I did this work with some other people who are at Oxford, like two past Rosier and Kamal Dingo and Art Louis, so Professor Hugh. So basically, in practical AIT, you want to measure like the complexity of distributions, like how predictable they are, minimum description length. You want to approximate Kolmogorov complexity. And one way of doing that is using compression algorithms. So stuff like limp-ziv or context-free weighting, for example. And one question that we had in this kind of research is, what's the difference between different complexity measures? And which one should you use? So most strings are incompressible, which means that compression algorithms don't really compress them. So, which is very important, because what we really want to understand is how well the different complexity measures and compression algorithms work on compressible strings, which are a very small subset of all strings. So first option is to look at how different complexity measures compare on sampling random strings. But this only works for very short lengths where you can actually sample very low complexity strings. Second option is to compare complexity measures on real data, but real data also has different biases, and results that apply for one data set might not generalize to another. So we found a third way of comparing complexity measures, which is sampling strings at every complexity level and comparing them on those. So for that, we use something called a nested neutral set estimator, which is a Monte Carlo Markov chain kind of algorithm. Basically, let's say Kx is a complexity measure, so something that approximates Kolmogorov complexity, like limp-ziv. Then it can take a range of values, either continuous or discrete, but you subdivide the space into a range of complexity values, K0 up till Km. And you initialize a population of strings, X0 up to Xm, such that every string Xi is in this complexity level, is in the complexity level of Ki, which means it has a complexity at most equal to Ki. And to sample random strings at different complexity levels Ki, you basically let this population evolve forward in time like a random walk. So you have n+1 strings. Every time step, you mutate each of the strings, which is by changing one bit, using one bit flip. And then you calculate the complexity there. And if it's still in the same level Ki, then you keep the new string. If it's not, then you keep the old string that was at that level. And also, if a string has a complexity that's lower than its complexity level, you can also swap it with the string that's at the lower complexity level. So you have two actions, which is mutation and swapping. And mutation is basically random walk, and swapping is basically parallel tempering in this this field, which basically allows you to escape local minima and explore space better. So you can use the frequency of swaps to calculate the size of each complexity level, how many strings have complexity at most equal to Ki. And you can also sample record Xi, the Xi strings at different points along the run. And this will give you a way of sampling strings at certain complexity levels. And basically, the theory says that this should reach a stationary distribution, which is a uniform distribution over every string at that complexity level. And it should be like an ergodic process, which means that after some amount of time, it's basically like a uniform distribution on all strings at every complexity level. So we first implemented the method and we tested it out on very short lengths where we can validate the results using exhaustive sampling. So this is for length 30. We looked at 3 different complexity measures, limp-ziv 78, limp-ziv 76, and CTW. We used depth equals 20 to make for faster calculations, but yeah. And we found the true distributions, and we ran NNSC for a different amount of time. So 10,000, 100,000, 1 million steps. And basically, all of these were sort of able to find the true distribution up to some error. And as we sort of like went longer, the error decreased. By the time we do like 1 million steps, the fit is basically almost perfect. Even though there are, let's say, 1 billion strings and we sample like, let's say, like less than 1% of them, we still get very accurate results. So we did different things with NST. The first thing we did is we compared different complexity measures against block entropy, where block entropy sort of tries to calculate like how often each substring appears in a string. So like it looks for patterns. Shannon entropy is like how often each 0 appears or each 1 appears. And block entropy is like how often each substring of size 2 or 3 appears, like how often does 0, 1, 0 appear in the text. So what we did is we sort of sampled strings from complexity levels for these different complexity measures. And then we found their block entropy values. For block entropy 1, which is Shannon entropy, what we found is there are a lot of strings that have very high Shannon entropy, but very low complexity. The simplest one being like 0, 1, 0, 1, 0, 1 repeat. So this method is able to find strings like that. And as the block entropy width, like as the, so width basically is the size of the sliding window, like the size of the substrings we look for. And as we look for bigger substrings, block entropy becomes closer and closer to all of these complexity measures. It becomes like more linearly correlated, especially for CTW, not as much for 78. And we can also compare complexity measures against each other directly. So, and this comparison is like a data agnostic way. So we just generate strings using random sampling. And after the system sort of like evolves for a given amount of time, it should be like a good sampler of simple low complexity strings and strings across any complexity level. So here are shown 5 different complexity measures, like there's block entropy, context-free weighting, Limp-Positive 76, 78, and BDM, the block decomposition method. So one thing to notice is when we generate strings with low block entropy, all of the complexity measures also assign low complexity to those low block entropy strings, which means that all these complexity measures are very good at picking up on like repetitions of substrings. They're very good at picking up on those types of patterns, which makes sense because like in information theory, we often think about, we prove results about the source entropy of distributions, and we prove things like compression algorithms sort of converge to it. And here's like a good visual illustration of that. But we can also compare complexity measures against each other. So we can see, for example, how similar Limp-Positive 76 is to CTW. And these plots are asymmetric because here we sample strings, typical strings from that Limp-Positive 76 considers to be this complex. And there we sample strings that CTW considers to be that complex. So we look at typical strings at each complexity level for that measure. So for example, here we find that any strings that CTW assigns this complexity to, Limp-Positive also assigns a very similar complexity to it. Whereas for Limp-Positive 76, some strings that Limp-Positive 76 give a high complexity to, CTW gives a lower complexity. And also there's like a slightly bigger variation for low complexities. And we can discover like these, so you can see these kinds of like very fine-grained patterns. You can see like these kinds of patterns and correlations for length 200 binary strings. And this would be impossible to see with exhaustive sampling or with like random sampling, because all we would get would be strings at this part, which is a very small subset of the space. So we can also look at different lengths. So we can see, for example, how the distribution of how many strings are there at, let's say, this Limp-Positive 76 complexity level, how that scales with length. And we find very irregular patterns. For longer lengths, NNSC starts giving less accurate results because it's much harder to explore the space. It takes much more time. But for shorter lengths, we did like 8 different runs for each length, and the results are very consistent, which gives us confidence that this is indeed what the distribution looks like. And we can also do this for different measures. For Limp-Positive 78, we can also calculate what the distribution should be exactly, which is a nice result in the literature. So we can validate against that. For 78, we capture the intermediate regime very well, but then we don't capture this regime as well. And we can also see that, so by doing different runs, we can sort of tell that limp of 78, it's not quite converging at the lower level because there's variation between runs. We can also see it by comparing against the exact distribution. And the reason for this is sensitivity, we believe. So sensitivity means, let's say you change one single bit in a string, how much does the complexity change? So we find that NNC works well for complexity measures which have very low sensitivity. So we're changing just one bit, still gives a very similar complexity value. Whereas for limpos of 78, if you take a random string that has low or intermediate complexity, and you just change one bit, the complexity varies wildly. So you can have a very simple string, but you just change one bit and the complexity goes very high. And the X and Y values here are the same on this plots. So that means that NNSC sometimes struggles it gets trapped in like local minima because it doesn't find the mutations that lets it go down to lower levels because the complexity measure is so sensitive to small changes. But sometimes it also performs really well for like CTW, which has very low sensitivity. And you also had to measure sensitivity by averaging over the entire complexity range. So if you just look at the random strings, like typical strings, you'll observe very low sensitivity. But actually, if you look at strings with lower complexity, the sensitivity increases by a lot. So that's what's really important for this method to work is low sensitivity in the intermediate complexity regimes. So CTW has very low sensitivity, and that's why we can actually get really good results for CTW. We do, for example, one thing we noticed is comparing CTW against different block entropy widths. We don't just see one linear line, but we also see different lines, which are sort of like different regions of high density of CTW versus block entropy. And we don't know the reason behind this. I didn't think that much about it, but it's a very interesting property. So if one of you want to think about why that happens, like theoretically, I think it's like a fun problem. Another thing we notice is very continuous, very predictable spikes in CTW. So it's mostly a continuous measure, like probability is sort of like, that probability of complexity K, number of strings with complexity sort of goes like 2 to the K. So CTW has that feature property very well, but also there are these periodic spikes. And the period seems to get lower as complexity increases and the amplitude gets lower, but they're very regular. And we observe them like even when we do different runs, we observe the peaks at the exact same places, which indicates that this is like an actual property of CTW. So yeah, so like conclusions, NSC can be used to understand properties of different complexity measures, and it works especially well for measures that are non-sensitive like CTW. We show like how to use this to compare different complexity measures, how to like find their distributions. And we believe that NSC can be generalized to other input-output maps as well, besides just these complexity measures that we looked at. And yeah, these are some resources. And yeah, you have any questions?